Have you ever stopped to think about the hidden rules? The ones that silently govern the cutting-edge technologies we see popping up all around us. We might, drive past a hydrogen fueling station or read about hydrogen transport, but we rarely consider the incredibly detailed safety standards working behind the scenes. It's this whole hidden world of precision. Today, on the Deep Dive, we're pulling back the curtain on one of those foundational documents. It's the National Fire Protection Association's Hydrogen Technologies Code, specifically the 2016 edition of NFPA 2.
Right. And our mission today really is to unpack this. It's a dense document, very technical, but we want to pull out the critical insights, the practical stuff for handling hydrogen. And that covers both its forms, the compressed gas, which the code calls GH2, and the super cold liquid form, LH2. What's really fascinating, I think, is how this one single document underpins so much safety for such a versatile energy source. It touches almost everything.
It really does. It acts as this fundamental safeguard, doesn't it? Covering everything from, well, generating the hydrogen in the first place.
Exactly. Generation, storage, the piping systems, which are complex, how it's used, how it's handled day to day.
Across all sorts of applications.
Yeah.
Stationary power, portable gadgets, and, of course, vehicles. That's the one most people are starting to see.
Yep. So you can really think of it as the ultimate safety manual for hydrogen. They've tried to cover all the bases, to prevent hazards.
And what's really unique about this code, something that jumped out at me, is how it was put together. It wasn't just written from scratch, was it?
No, that's a key point. It's largely compiled, pulled together from lots of other established NFPA standards. Things covering, say, fuel systems for vehicles or general rules for compressed gases and cryogenic fluids.
But then they tailor it specifically for hydrogen.
Precisely. They adapt it. And the level of detail is amazing. They actually change the terminology. So generic compressed gas becomes GH2 everywhere. Cryogenic fluid becomes LH2. And the sources make it clear any changes they made to the text they pulled in are shown right there in brackets. If they just deleted something, that's Mark II. It shows incredible precision, a real focus on hydrogen's specific needs.
Okay, so if these are the rules keeping things safe, who actually writes them? Who are these architects of safety? It's not just some government agency working alone, right?
Not at all. And that's what makes it so robust, really. The committee that drafts these codes is incredibly diverse. It's not theoretical. It's a team effort, bringing together a huge range of expertise. Our sources list members from, well, all over the place. You've got manufacturers directly involved, companies like Bethlehem, Hydrogen, Proton Energy Systems, Toyota, Nuvera Fuel Cells, even Shell Oil.
So the people actually making and using the hydrogen tech are at the table.
Exactly. That ensures the code is practical, that it considers real-world manufacturing and use cases. Then you have the regulatory and enforcement side. People from the U.S. Department of Transportation, the Calgary Fire Department, the Michigan Bureau of Fire Service. These are the folks on the ground, the ones enforcing the rules, inspecting facilities, responding if something goes wrong. Their input is vital for making rules workable.
Makes sense. Who else?
You also have independent experts and consultants. Firms like Kazarians and Associates, code consultants. They bring external scrutiny, specialized engineering knowledge, and, critically important, there's a strong contingent from research and testing institutions. Places like United Technologies Research Center, Southwest Research Institute, NIST, Sandia National Labs.
The science side.
Right. They bring the scientific rigor, the latest research, the hard data from testing. That ensures the code is based on sound science, not just guesswork. And finally, you have industry associations like the Compressed Gas Association, representing broader industry standards and making sure everything aligns.
Wow, that's quite a mix. So how does this diverse group actually create the code? You said it's compiled.
Yeah, the process itself is really rigorous. Like we mentioned, they extract relevant sections from other NFPA documents, NFPA 52, 55, 8 or 53, and others. Then they modify that text, sometimes deleting parts, always marking the changes clearly. After all that careful compiling and tailoring, the draft goes out for ballot to the entire committee. Every member gets to review, comment, vote. It's this collaborative back-and-forth process.
So everyone gets a say, basically.
Exactly. That multidisciplinary approach forces critical thinking from all angles. It helps ensure the final code is comprehensive, practical, and scientifically sound. It really relies on that shared expertise.
Okay, that sounds incredibly thorough. But what about progress? What happens if someone develops a new hydrogen system or safety device that's actually better, maybe safer than what's written in the code? Are they stuck?
That's a really important question. And the code anticipates this. There's a specific section called equivalency, section 1.5. It explicitly says the code isn't meant to block the use of systems, methods, or devices that are of equivalent or superior quality, strength, fire resistance, effectiveness, durability, and safety compared to what's prescribed.
Ah, so there's a pathway for innovation.
Yes, definitely. It acknowledges that technology moves fast and safety can improve, but, and this is crucial, it's not a free-for-all. To use something under the equivalency clause, you need to provide solid technical documentation, proof that your new approach really is equivalent or better.
And who decides if the proof is good enough?
That falls to the authority having jurisdiction, the AHJ. Usually that's your local fire marshal or building code official, the regulatory body overseeing that specific project. They review the documentation and have to formally approve it.
So it's about fostering innovation, but within very strict safety boundaries, not cutting corners.
Precisely. It's a smart mechanism to allow progress while keeping safety paramount. It's a really important balancing act.
So putting it all together, what this tells us, what it means for you listening, is that this code isn't some static relic. It's a living document. It's designed to evolve, balancing robust safety rules with the need to adapt to new technologies. Okay, before we dive deeper into the specifics, we really need to get a handle on the language. Like any technical field, this code uses very precise definitions, and getting these right is crucial for understanding the safety measures.
Absolutely. Chapter 3, the definitions chapter, is foundational. Let's touch on a few key ones that come up again and again. First, and probably the most fundamental distinction, is GH2 versus LH2, gaseous hydrogen versus liquefied hydrogen.
Right, gas versus liquid. Seems simple, but why is it so important here?
Because their physical properties are vastly different. LH2 is cryogenic, incredibly cold, and behaves differently than GH2 gas under pressure. This means different hazards, different storage, different handling requirements. The entire code pivots on this distinction.
Got it. Okay, what else? I saw labeled and listed mentioned frequently. Are they just fancy ways of saying approved?
Not quite. They have very specific meanings here that imply a higher level of scrutiny. Labeled means an approved third-party organization has put its mark on the equipment, signifying it meets standards, and that organization periodically inspects the product's manufacturing. Listed is similar, but often broader. It means the equipment is included in a list published by such an organization, again, implying periodic inspection or evaluation, and stating it meets standards or is suitable for a specific purpose.
So it's about independent verification and ongoing checks, not just a one-time approval.
Exactly. It provides a significant layer of assurance. Then there's control area. This helps manage hazards spatially. It's a defined part of a building or an outdoor area where hazardous materials like hydrogen are allowed, but only up to certain limits, the maximum allowable quantities, or MAQ. It helps zone the risks.
Okay, delineating the danger zones. What about materials? I saw different terms for things that burn.
Right. The code distinguishes between combustible, non-combustible, and limited combustible material. It's not just a simple yes-no on burning. It's about how something burns, its heat potential, its flame spread characteristics. A limited combustible material, for example, might not be fully non-combustible, but has a defined lower heat value and specific flame spread limits. This is vital for choosing construction materials near hydrogen systems.
Affects fire barriers and things like that.
Precisely. Then there's purge, a critical safety step. It means replacing a flammable atmosphere or one with too much oxygen with an inert gas until it's non-flammable, essential before introducing hydrogen into a system or furnace. And the annex adds nuance here. High oxygen-bearing atmosphere is relative. In some special furnace applications, purging might mean getting oxygen down to just 1–3%, shows the extreme care needed.
Wow, okay. And vaporizer. That sounds specific to liquid hydrogen.
It is. It's just a heat exchanger that turns the cryogenic LH2 back into GH2 gas so it can be used. The heat can come from ambient air, steam, whatever's available.
Simple function, critical component for LH2. Lastly, you mentioned pressure definitions.
Yes, several key ones. Absolute pressure, maximum allowable working pressure, or MLWP, operating pressure, overpressure. They sound similar, but the distinctions matter for design and safety margins. For instance, the MAWP for GH2 fueling systems has a built-in safety factor. It's calculated as 1.1 times 1.25 times the normal service pressure.
So it has to be able to handle significantly more pressure than it usually sees.
Over 35% more. It builds in a substantial safety buffer against unexpected surges or conditions. It's proactive protection.
These definitions clearly aren't just academic. They are the absolute bedrock for every safety decision, every engineering choice in the hydrogen world. But NFPA 2 goes beyond just rules and definitions. What I found really interesting is how it explicitly lays out its philosophy, its goals and objectives for safety. It tells you why it's doing what it's doing.
That's right. Chapter 4, General Fire Safety Requirements, really gets into this. The overarching goals are stated pretty clearly. Provide a reasonable level of safety, property protection, and public welfare from fire, explosion, and other hydrogen hazards. It's about finding that balance, enabling hydrogen use while ensuring robust protection.
And beneath those broad goals.
More specific objectives. For safety, the objective is explicitly reducing the probability of injury or death from hydrogen-related incidents. But it also includes things like protecting building occupants from structural failure caused by an incident, and even limiting unacceptable interruptions to a facility's function, especially if it serves the public.
So it considers the ripple effects, not just the initial event.
Exactly. The code also works from stated assumptions. These are like the ground rules for risk assessment. For example, it generally uses a single hazardous material release assumption.
Meaning they model one major failure at a time.
For initial design, yes, though more complex scenarios can be looked at. But importantly, it also assumes external forces like a fire next door or an explosion elsewhere can impact the hydrogen system. So designers have to protect against outside threats too.
That makes sense. Now, you mentioned flexibility earlier. How does the code allow for different situations?
Through its compliance options. This is key. A facility basically has two paths to show they meet the code. First is the prescriptive-based option. This is the traditional route. Follow chapters 1 through 4 and 618 exactly as written. Do what the book says. It's clear, defined.
The standard approach.
All right, but then there's a performance-based option. This allows for more tailored engineered solutions. Instead of just following the rules, you have to demonstrate through detailed calculations, modeling, and analysis that your specific design meets the overall goals and objectives of the code.
So more complex requires more proof.
Yes, definitely. It often involves third-party review and is usually used for more complex or unique installations where the standard prescriptive rules might not fit perfectly or might stifle innovation. It allows flexibility while demanding rigorous proof of safety.
And part of this overall safety picture is planning for things going wrong, right?
Absolutely. An emergency plan is mandatory for any facility handling hydrogen above certain quantities, and it has to be detailed. Location of emergency equipment, testing schedules, hazard labels, posted procedures, safety data sheets readily available, and critically trained liaison personnel who can effectively communicate with the fire department during an emergency. Proactive planning is vital.
Let's dig a bit more into that performance-based option. It sounds like a lot more work, but potentially more rewarding for complex projects. How does that work in practice?
Well, the annex material actually points to established engineering guides, like the SFPE engineering guide, which outlines a detailed process. It's often a 10-step approach. It involves things like clearly defining the project scope, identifying the specific safety goals and objectives you need to meet, developing very specific performance criteria.
So measurable targets for safety.
Exactly. Then you develop different design scenarios. What happens if this fails? What if there's a fire here? You create trial designs and rigorously evaluate them against those scenarios and criteria using calculations and modeling. Finally, you select the design that best meets the safety objectives, often involving all the stakeholders, designers, operators, regulators in the decision. It's a very thorough analytical process.
And I saw something about safety factors being required in these designs.
Yeah.
Yes, that's crucial. Performance-based designs must include approved safety factors. These are basically multipliers applied to calculated results, like predicted temperatures or pressures. They're there to explicitly account for uncertainty in the assumptions made, in the data used, in the models themselves. So if a model predicts a peak temperature, the design might need to handle that temperature plus, say, 50%, just to be safe.
Building in a margin for error, essentially.
Yeah, precisely. And the code requires a sensitivity analysis to figure out appropriate ranges for these factors, understanding how sensitive the outcome is to different variables. It really underscores the scientific rigor involved and acknowledges that real-world conditions aren't always perfectly predictable. It's about building resilience.
It's really clear that safety under this code isn't just about ticking boxes. It's about deeply understanding the risks, the why behind the rules, and having robust frameworks, whether prescriptive or performance-based, to manage those risks effectively. Okay, with that philosophical and structural understanding, let's get into the real engineering details. How is hydrogen actually handled safely day to day? Let's talk containment, detection, piping. the nuts and bolts.
Right. This is where Chapter 6, General Hydrogen Requirements, and Chapter 7, Gaseous Hydrogen, come in. First up, containment. It's fundamental. Hydrogen has to be stored in cylinders, containers, or tanks that meet strict design and construction standards, usually from the Department of Transportation, DOT, Transport Canada, or the ASME Boiler and Pressure Vessel Code. These are internationally recognized standards.
And they treat even partially full containers as full.
Yes, that's a key point. Any container with residual gas is considered full for safety purposes. No cutting corners just because it's almost empty. It ensures maximum precautions are always taken. Pressure relief devices are another non-negotiable. They're vital for protecting containers from rupturing if the internal pressure gets too high, especially, say, if the container is exposed to a fire.
Just a safety valve, basically.
Essentially, yes. And a small but important detail. Pressure relief valves, specifically for GH2 service, aren't allowed to have manual lifting devices. Prevents accidental opening. Security is also mandated. Hydrogen systems need to be secured against being accidentally knocked over or dislodged. And crucially, they must be protected from unauthorized access.
Keeping unqualified people away.
Exactly. Storage and use areas need to be secured. Then there's separation from hazards. Hydrogen systems have to be kept away from incompatible materials, things that could react dangerously, and away from ignition sources. The code gets specific. Keep combustible waste, dry vegetation, things like that, at least 10 feet away. Though interestingly, you can sometimes use a fire barrier wall instead of distance if space is tight, provided the wall is built correctly.
Practical considerations. What about the pipes carrying the hydrogen?
Piping systems get a lot of attention. They have to be designed for the specific pressure and temperature ranges they'll see in service. They also need to accommodate physical stresses, expansion, contraction, vibration, even potential ground settlement, and definitely fire exposure. And there are material restrictions. Gray iron, ductile iron, cast iron pipes and fittings, absolutely forbidden for GH2 fueling applications due to potential embrittlement issues under pressure.
Material science matters. What about underground pipes?
The preference there is for welded construction, and crucially, no valves or unwelded mechanical joints buried underground. You want to minimize potential leak points that are hard to find and fix. Cleaning and purging is another mandatory step. Before you first use a hydrogen system, or if you change the service, or after repairs, you have to clean it thoroughly and purge it, usually with an inert gas.
To get rid of air or contaminants that could cause an explosion.
Precisely. Prevents forming those dangerous mixtures. Now, GH2 detection systems are a critical layer of safety. The equipment itself has to be listed or approved, and it needs rigorous design, installation, testing, inspection, calibration, and maintenance, all following the manufacturer's instructions and the listing requirements.
How often does it need testing?
At least annually is the minimum requirement in the code. But the annex material strongly recommends doing it more often, maybe quarterly, especially when a system is new or if it's in a harsh environment. And you have to keep detailed records for 3 years. And here's that practical limitation we hinted at earlier. The annex points out that detecting hydrogen leaks outdoors or in large open areas can be challenging for fixed gas detectors.
Because the gas disperses so quickly.
Exactly. They're most effective when the sensor is inside an enclosed space where the gas might accumulate. It highlights the need for other safety measures or careful sensor placement outdoors.
Good to know. What about these hydrogen equipment enclosures, HEEs?
Right. These are required if you have more than a certain amount of hydrogen over 1,000 standard cubic feet, or if the enclosure houses processing or generating equipment. These HEEs need specific safety features, things like emergency shutoff valves that automatically close if power is lost, and mandatory ventilation systems to prevent gas buildup. They also need an emergency shutdown system, an ESS. This ESS has to activate automatically if the GH2 detectors go off, if there's a fire alarm, or if the ventilation system fails.
So multiple triggers for shutdown.
Yes, and specifically if hydrogen concentration hits 25% of the lower flammable limit, that's LFL, the minimum concentration needed to ignite, the ESS must activate immediately, and a visible alarm has to light up outside the enclosure.
25% LFL seems quite sensitive.
It is. It provides an early warning and shutdown well before the concentration reaches the actual flammable level, which is typically around 4% hydrogen in air. It's about intervening early.
So taking all that together, it's clear that handling hydrogen safely involves layers upon layers of protection. Engineered systems, specific procedures, constant monitoring, and built-in safeguards. It's a comprehensive approach. Let's zoom in now on probably the most visible hydrogen application for many people, vehicle fueling. We see these stations starting to appear. How does the code ensure safety when you're pumping highly flammable hydrogen gas often under high pressure, into a car.
Yeah, it's a complex operation, and chapters 10 for GH2 and 11 for LH2 go into incredible detail. The first thing is the sheer number of system component qualifications. It's a long list. Everything from the pressure relief devices, the gauges, the regulators, the valves, hoses, nozzles, all the way to the electrical equipment, gas detectors, the dispenser itself, even the breakaway devices that prevent a disaster if someone drives off while connected. All these must be individually listed or approved.
So every single piece has to meet a specific standard.
Exactly. It ensures the entire system, piece by piece, is designed and tested for hydrogen service. Then there's the piping and connections. All the pipes and tubing have to be suitable for hydrogen, obviously, but also for the pressures and temperatures involved. And they need a minimum safety factor of 3 built into their design.
A safety factor of 3, that sounds substantial.
It is. It means the piping must be able to withstand 3 times its normal operating pressure. And little details matter too. Threaded connections have to be perfectly free from burrs that could affect the seal. And a big one, mechanical connections in hydrogen piping cannot be buried.
Keep them accessible for inspection and leak checks.
Precisely. Now, one of the most active safety features is the integrity checks performed during the fueling process, actually before it really starts. The dispenser's control system automatically verifies the integrity of the whole connection.
Yeah.
The hose, the breakaway device, the nozzle, the connection on the vehicle itself.
How does it do that?
It pressurizes that section up to the vehicle's current back pressure and holds it, monitoring for any pressure drop for at least 5 seconds. If it detects a leak, it won't start fueling. And for higher pressure fills, like 350 bar, it repeats a similar check at 85% of the nozzle's service pressure during the fill. It's constantly ensuring the connection is sound.
That's really smart. Active monitoring.
It is. And an interesting side note from the annex, an older version of the code used fixed pressure points for these checks, but they moved to percentages like 85% to achieve greater standardization and consistency across different fueling system designs. Shows that evolution in practice.
What about signage?
Placarding is mandatory, especially for bulk storage. Sites with liquid hydrogen, LH2, need clear signs. Warning: liquefied hydrogen flammable gas, no smoking, no open flames. Very direct.
And where can these fueling stations be located? Indoors, outdoors?
There's a strong preference for outdoors. Indoor public fueling for LH2 is flat out prohibited, and indoor public fueling for GH2 is currently reserved in the code, meaning the standards haven't been developed yet to consider it safe for the general public.
Why the preference for outdoors?
Dispersion. Hydrogen is lighter than air and disperses very quickly outdoors, reducing the risk of accumulating an explosive mixture. Indoors, containment is a much bigger challenge.
Makes sense. Now, you mentioned something fascinating earlier about the fueling pad itself, the ground the car sits on.
Yes. This is one of those surprising details that shows the depth of thought. The vehicle fueling pad has to be concrete, or another material with an electrical resistivity not exceeding 1 megaohm.
1 megaohm. Why such a specific electrical property for concrete?
To dissipate static electricity. It prevents static charge from building up on the vehicle during fueling, which could potentially cause a spark.
Wow. Was there an incident that prompted this?
Apparently, yes, but indirectly. The source material mentions incidents in Europe at gasoline stations where they used a new type of non-absorbent polymer paving material. It was great for preventing gasoline spills from contaminating the soil, but it had very high electrical resistance.
And that caused static problems.
Exactly. Static built up and caused issues. So, learning from that gasoline experience, the hydrogen code proactively mandates a conductive pad material to prevent a similar static discharge hazard with highly flammable hydrogen. It's a brilliant example of cross-fuel safety learning.
That is fascinating. Okay, what about emergency systems at the station?
A comprehensive emergency shutdown system, ESS, is absolutely required. There must be clearly marked manual push buttons to activate it. And critically, if any detection system activates gas leak, liquid leak, flame detection, it must automatically stop all dispensing and close the main emergency shutoff valves.
Automatic shutdown is key.
Absolutely. And after any emergency shutdown, whether manual or automatic, the system requires a manual restart by trained personnel. No just slipping back on. Human oversight is required before resuming operations.
The level of detail here is just incredible. From the material science of the piping to the electrical properties of the concrete pad, every angle seems considered for safety at these fueling stations. Beyond vehicles, hydrogen plays crucial roles in specialized industrial settings and research labs. How does the code tailor safety for these often unique environments?
It does, with dedicated chapters. For fuel cell power systems, Chapter 12, whether portable or stationary, the systems themselves or their key components generally need to be listed or approved. For stationary systems, the hydrogen storage part has to comply with another specific NFPA standard, NFPA 853. It ensures consistency. For hydrogen generation systems, Chapter 13, things like interconnecting piping need to meet established industrial piping codes, like ASME B31. Siting is also critical, maintaining proper separation distances based on the amount of hydrogen and potential exposure risks.
Any restrictions on where these generators can be placed?
Yes, a significant one. Hydrogen gasifiers are generally not allowed on rooftops or in penthouses of occupied buildings. The only exception is if the specific unit is listed and approved precisely for that kind of rooftop installation. It's about preventing a major hazard right above occupied spaces. And an interesting industrial use mentioned in the annex. Large electrical generators often use hydrogen internally for cooling. It reduces friction and improves efficiency. These systems, of course, need careful design, too.
Okay, what about those special atmosphere applications? Sounds like industrial furnaces.
Exactly. Chapter 15 covers this, primarily focusing on furnaces using hydrogen atmospheres. Safety is paramount here. The furnace and any entry-exit vestibules must be purged with an inert gas before hydrogen is introduced.
Getting all the air out first.
Right, to prevent an explosion. You also need active ignition sources. Burn off pilots at any openings where the hydrogen atmosphere meets the outside air, like vents or doors. These pilots immediately burn off any escaping hydrogen safely. And for hydrogen, which is lighter than air, the annex advises placing these pilots at the top of any opening. Also, all the safety interlocks on these furnace systems, the automatic checks and balances, must be functionally tested at least once a year.
Ongoing verification. Makes sense. What about labs? Chapter 16.
Labs have comprehensive requirements. Fire protection include automatic sprinkler systems, specifically quick response types, fire alarms linked to emergency responders, standpipe and hose systems, and portable fire extinguishers. A layered approach. Cylinder safety is heavily emphasized. Only trained personnel should handle cylinders. And here's that critical rule again worth repeating. Never rely on the color of the cylinder to identify the contents.
That seems so counterintuitive but vital.
It really is. Labels are the only reliable identifier. The code also mandates using proper pressure-reducing regulators with two gauges, high and low pressure, and specific procedures for purging connections safely, especially with flammable gases. Fume hoods are essential in labs. They need continuous airflow monitoring with alarms. Their location matters, keep them away from high-traffic areas or drafts that could disrupt the airflow.
And the exhaust needs to go somewhere safe.
Yes, the exhaust stacks typically need to extend at least 10 feet above the roofline to ensure proper dispersion. They even specify checking exhaust fans to make sure they aren't accidentally running backward. It's that detailed.
It really shows how the fundamental principles of hydrogen safety containment, purging, detection, train handling are applied consistently but tailored to the specific risks of each environment, whether it's a power plant, a factory furnace, or a research lab. Given hydrogen's well-known flammability and its potential to form explosive mixtures, understanding and controlling explosion hazards is absolutely critical. The code delves into this in detail, doesn't it?
It certainly does. While Chapter 9 itself is marked reserved in this edition, Annex K provides extensive voluntary guidance on hydrogen explosion control, likely foreshadowing future mandatory requirements. And Annex G offers valuable insights specifically for labs. The code discusses the different types of explosions. It distinguishes between deflagrations, which are essentially very rapid burning, with the flame front moving slower than the speed of sound, and the much more dangerous deflagration to detonation transition, or DDT.
Detonation being a supersonic explosion.
Exactly. It creates a powerful shockwave. Achieving DDT is complex and depends on many factors, but the potential is there, especially with hydrogen. What's really fascinating, and maybe not obvious, is the impact of congested spaces. Things like dense arrays of pipes or multiple pieces of equipment packed closely together can dramatically increase the severity of an explosion. This congestion creates turbulence as the flame front moves through it. This turbulence accelerates the flame, causing pressure to build up much faster and potentially leading to that dangerous DDT. The annex gives specific criteria for identifying potentially hazardous congestion based on spacing.
So layout matters immensely.
Hugely. The code also differentiates between unconfined and partially confined explosions. Truly unconfined explosions in open air usually require a very large release of hydrogen to be significant. But Partially confined explosions, say, inside a building or even just within a dense equipment area, are a bigger concern. Their severity depends on concentration, ignition, how confined it is, and those obstructions we just talked about. And even a small explosion in a small enclosed space can create what's called sustained overpressure, which can be more damaging than a short, sharp blast with the same peak pressure because it pushes on structures for longer.
The duration matters as much as the peak force.
Right. And the discussion of blast effects is sobering. The code mentions that an explosion equivalent to just a tiny fraction of a gram of TNT can rupture eardrums at close range. And minor structural damage to buildings can happen at surprisingly low pressures, less than 1 psi, enough to break windows and create dangerous flying debris.
And here's something that really struck me as alarming from the annexes.
What's that?
It points out that even 0.4 volume percent hydrogen in an enclosure that's only 1/10 of the lower flammable limit, way below what normally ignites, could, under the right confined conditions, potentially cause minor damage and injuries from the pressure pulse.
Yeah, that's a stark reminder. It shows just how energetic hydrogen is and how dangerous even seemingly non-flammable concentrations can be if confined and ignited strongly enough. It really underscores the hazard potential.
So how does the code approach preventing these explosions?
The primary explosion prevention strategy is proactive avoidance. A key piece of guidance is don't intentionally release hydrogen into areas with congested piping or equipment where flame acceleration could occur. Design the layout to minimize this risk from the start. When prevention isn't enough, you need explosion protection measures. The annexes list several options: limiting the quantity of hydrogen in one place, using active systems like explosion suppression or high-speed deluge sprinklers, providing explosion venting.
Venting directs the blast somewhere safe.
Ideally, yes, away from people and critical structures. Other measures include using explosion-resistant equipment or enclosures, using remote controls to keep personnel away, conducting hazardous operations in isolated buildings or outdoors, and providing blast-resistant walls or barricades, especially in labs.
And a crucial warning about labs.
Yes. A standard laboratory fume hood does not provide protection against explosions. That's critical for researchers to understand.
What about designing buildings or equipment to actually withstand a blast?
That's explosion-resistant construction. It's required for scenarios with a higher potential blast yield. It has to be specifically engineered for the anticipated blast wave, the peak pressure, how long it lasts, and also for potential missile hazards.
Things getting thrown by the explosion.
Exactly. Fragments can travel incredibly fast, thousands of feet per second. The design needs to account for the material, mass, shape, and velocity of potential missiles. The code even gets into specifics like shield design for viewing windows, suggesting laminated designs with glass on the outside to blunt missiles and polycarbonate on the inside to contain shards and resist the pressure wave. It's highly specialized engineering.
It truly highlights the immense destructive potential of hydrogen if things go wrong, and the incredibly sophisticated, multi-layered engineering required to safely contain that potential. Safety is clearly not optional here.
So we've talked about the code, the engineering, the systems. But all of this relies on people, right? The human element seems absolutely critical for making these safety systems work. Absolutely critical. You can have the best engineered system in the world, but if the people operating and maintaining it aren't properly trained and diligent, safety is compromised. Annex H on general hazards and various sections throughout the code hammer this home. First and foremost, train users. The code is explicit. Never let anyone use or connect a cylinder to any system unless that person is trained and knowledgeable. Trained in the dangers of pressure, the chemical properties, the right equipment connections like CGA fittings, it's non-negotiable.
Competence is key.
Absolutely. And speaking of cylinders, that crucial point about cylinder identification, it bears repeating. Do not use a compressed gas cylinder unless the cylinder is clearly marked or labeled. Reject any cylinder that is unmarked or has conflicting markings. Never rely on the color of the cylinder to identify the contents.
Because colors aren't standardized.
Exactly. Relying on color is a recipe for disaster. If there's any doubt, don't use it, return it. It's a simple rule, but potentially life-saving. Basic eye protection is also mandated whenever working near compressed gas systems. A constant reminder of the physical hazards.
And what about emergencies? We mentioned emergency plans earlier.
Yes, and emergency plan training is essential. Everyone involved in operations needs to be trained on what to do in an emergency, including how and when to activate emergency controls, often before evacuating, to contain the situation if possible. This training isn't a one-off. It needs to happen whenever new hazards are introduced or procedures change. And importantly, local emergency responders also need specific training to handle hydrogen incidents safely and effectively.
It's about preparedness across the board. What about keeping the equipment itself safe over time?
That's maintenance. The CUN requires formal, scheduled maintenance and retesting activities. All of this must be documented, and the record's kept for at least 3 years. For LH2 systems specifically, maintenance should follow the manufacturer's recommendations, but happen at least every 6 months.
And these aren't just quick checks, are they?
No, an Annex F, provides examples of detailed maintenance checklists. It includes things you check daily or at startup, like alarm signals, weekly checks, like testing certain lines, and more extensive periodic checks. These periodic checks involve inspecting igniters, pressure switches, control valves, checking equipment cleanliness, functionally testing pressure relief valves, lubricating parts, verifying all safety interlocks are working correctly. It's a continuous methodical process.
So the takeaway here is pretty clear. Even with incredibly sophisticated technology and detailed codes like NFPA 2, the ultimate safety net relies on human factors. Vigilance, rigorous training, meticulous procedures, and ongoing maintenance are what make the whole system work safely. Well, today we've taken a really deep dive into NFPA 2, the Hydrogen Technologies Code. We've journeyed from understanding the diverse group of experts who craft these intricate rules.
Bringing together manufacturers, regulators, researchers, all pooling their knowledge.
Right. We explored the core philosophy of safety, the goals, the objectives, the assumptions that underpin everything. We saw how it balances prescriptive rules with flexible, performance-based options.
We got into the engineering marvels of containment, the importance of precise definitions, the sophisticated detection systems, and those surprising details, like the conductive fueling pads.
Learned from gasoline incidents, remarkably, and that vital rule about never trusting cylinder colors.
We also confronted the sobering reality of explosion hazards and the incredible engineering needed for protection.
And finally, we underscored the absolute necessity of the human element. Thorough training, strict procedures, diligent maintenance. It's clear this code isn't just regulations on paper. It's a testament to a massive, ongoing effort to safely integrate hydrogen into our world.
Exactly. It's about balancing the huge potential of hydrogen as an energy carrier with an unwavering commitment to protecting people and property. It's a framework for responsible innovation.
So thinking back on our discussion, what stands out most to you, our listener? Maybe it's the sheer complexity involved in managing hazardous materials safely. Or perhaps one of those specific details, like the danger of even tiny hydrogen concentrations, or the multi-step integrity checks during fueling. It certainly gives you a new appreciation for the hidden safety layers around us. And here's a final provocative thought for you to consider, something we touched upon indirectly. The NFPA 2 code itself notes that some of its own guidance, like separation distances for bulk hydrogen, draws upon, but also improves upon, much older OSHA tables based on data from way back in 1969. The code acknowledges these older tables have limitations, not fully aligning with modern construction or hazard analysis. So it makes you wonder, how much of our current safety infrastructure, particularly for new and emerging technologies, might still be influenced by historical data or assumptions that don't fully capture today's understanding or capabilities? And what does that imply for how we regulate the next wave of innovation, ensuring safety keeps pace with progress? Definitely something to think about. Join us next time for another deep dive, where we'll continue to unpack complex topics and make you well informed, one surprising fact at a time.